Hello, everybody. Happy Friday. So I was thinking about something funny before I started recording this, and this is like the bets that you should take during this lecture. One being, what is the chances that my kids are going to walk in at some point during this lecture? And then two is, what are the chances that I'm going to try to use the highlight feature and then forget to turn that off? So you can be looking out for those, and I will probably, find it quite humorous if either of those things happen. But anyway, so our goals for today are to keep thinking about the reactions of alcohols. So I'll recap where we left off on Wednesday, and then I'll also introduce some new reactions. So we'll learn about some alternative reactions to convert alcohols into alkyl halides. We'll also talk about the elimination reactions for alcohols, which are called dehydrations. And then depending on where we are at there, we might start the oxidation of alcohols, which is the last class of reactions that we need to cover for our exam coming up next week. Okay, so to recap where we were in class on Wednesday, we were thinking about the reaction of alcohols with HX, and remember that whether the alcohol was primary, secondary, or tertiary would affect the mechanism of that reaction. So primary alcohols generally went through an SN2-like mechanism after protonation of the alcohol, whereas tertiary alcohols went through an SN1-like mechanism after protonation of the alcohol. And secondaries, we were generally going to avoid using this reaction because they gave us a mixture in terms of mechanisms and products, and for that reason, we called them not very quote-unquote useful. Okay, so I just want to look at two example reactions, one of a primary, one of a tertiary, and then we'll talk about an alternative way to make alkyl halides from alcohols. Okay, so in our first example, let's look at this structure. Okay, so we're going to take this primary alcohol, and in this case, we'll react it with HBr. So remember, we'll first protonate the alcohol to turn it into a good leaving group, which would be water, and then our bromide could come in and attack and do the SN2 mechanism. Okay, and so in this case, as it relates to the position of the alcohol, it's primary, so we don't need to worry about the stereochemistry there. But I threw in this chiral center here at the benzylic position just to point out, if we had a chiral center existing somewhere else in the molecule, we wouldn't touch that. Okay, so let's look at one last example of this. Let's look at a related molecule, but let's move the position of the alcohol. So now let's make it this optically pure starting material. So optically pure meaning this single enantiomer. Okay, so up here we were looking at a primary, now we're looking at a tertiary alcohol. So again, remember that we are going to first protonate the OH, that turns it into a good leaving group in water, and then the leaving group leaves. And so to think about the intermediate here, we'll end up with this tertiary and benzylic carbocation. Okay, so remember that carbocation carbons, they're sp2 hybridized and trigonal planar, and so when our bromide adds to that carbon, it can do so from either face, and so even though we had this optically pure single enantiomer starting material, we'll end up with a racemic mixture in the tertiary bromide. Okay, so our bromide could attack the carbocation from the back, or the bromide could attack the carbocation from the top. So we would have this racemic mixture of tertiary bromides. Okay, and so for secondary alcohols, we generally will avoid this reaction, and instead we'll use the reaction we're about to talk about. So the next reaction to talk about is going to be the reaction of alcohols with a reagent called PBr3. So reaction of alcohols with PBr3. Okay, so PBr3 is phosphorus tribromide, and I'll write that out here in just a second. Okay, so let me give you the overall of the reaction, and then we will go ahead and talk about that reagent and think about some mechanistic issues related to some observations of this reaction. Okay, so in this reaction, we're generally going to convert our alcohol with PBr3 to form the corresponding alkyl bromide. Okay, so in this way, we're only making the bromide because phosphorus tribromide is a source of bromine and no other halogen. So this is specific to bromide. So first we could talk about PBr3. So this is called phosphorus tribromide. And then its structure is phosphorus with 3 bromines attached to it. Nothing too special there. As phosphorus is in the 3rd row in the periodic table, we're going to see that it can accommodate more electrons. And so we'll go ahead and think of that as an electrophile. We'll see that in the first step of the mechanism. Okay, so PBr3 is going to really serve two purposes in the mechanism, as we'll see. One is that it's going to allow us to basically activate the alcohol as a leaving group. The other thing is it's going to be our bromide source. Okay, so some key points about this mechanism. Okay, so this only works with methyl, primary, and secondary alcohols. Secondly, inversion of configuration is observed. So if you had a chiral alcohol, you would observe inversion of configuration. Okay, so it's stereospecific in that way. Okay, so given that we're observing inversion of configuration and this only works on methyl primary, excuse me, and secondary alcohols, we can predict what type of substitution mechanism this is undergoing. So we're doing a substitution, bromide is going to replace the OH, the hydroxyl group. So it's formally a substitution. So if we had to think about, what would be a likely mechanism here, SN1 or SN2, we have all the information to answer that question, right? So which one of the mechanisms, SN1 or SN2, goes through inversion of configuration? And which one of those mechanisms, SN1 or SN2, prefers unhindered electrophiles? So hopefully you answered SN2 for both of those. So those observations tell us that there is an SN2 mechanism operating here. Okay, and we're clearly not directly doing that on the alcohol, again, because OH is still a bad leaving group. So we'll see in the mechanism, we first activate the OH to convert it into a good leaving group. We'll see how that works, and then we'll proceed on with the SN2 step. Okay, and one thing just about the stoichiometry about this reaction. So PBr3 has 3 bromines or bromides. All 3 of them can be replaced in the mechanism, as we'll see. So really the stoichiometry would be 3 moles of our alcohol gives us 3 moles of our alkyl bromide with 1 mole of our phosphorus tribromide. Okay, so let's go ahead and look at the mechanism of this reaction with an example. Okay, so the example we'll use, let's look at a chiral secondary alcohol so we can see the stereochemistry within the mechanism. Okay, so PBr3, I'm gonna ignore the stoichiometry here. And so notice how, my OH was on a wedge, my incoming bromide nucleophile is on a dash, so we see that inversion of configurations. We can see from here to here, we've are observing this inversion. Okay, so what is the mechanism? So we know there's some sort of SN2 step going on because of the observations that we made about the reaction. And so let's figure out how that is possible. So, for an SN2 reaction, we need a good nucleophile, we need a good leaving group. Okay, so let's figure out how we're going to convert our alcohol into a good leaving group. Okay, so this is where phosphorus tribromide is going to play a role, is to first convert our OH into a good leaving group. So notice that phosphorus is attached to 3 electronegative bromine atoms. It also has a partial positive charge on it. And so that phosphorus is going to be an electrophile in this case, and we have the oxygen lone pairs to participate as a nucleophile. So let's imagine this substitution step, with respect to phosphorus. So at this point, all the chemistry is happening at the oxygen and the phosphorus. So we haven't touched the carbon that bears the OH yet. So that stereochem is still on a wedge. Okay, but notice this structure now. So now I have essentially this oxygen with a positive charge on it. So think about the previous reaction with HBr. We protonated the OH and that oxygen ended up with a positive charge. And so that when that group left as a leaving group, in that case it was water, it left as a neutral species. So now realize that this whole thing right here now is a good leaving group. Okay, so that whole group can leave, by breaking that carbon-oxygen bond. So let's draw that mechanistic step. So we also generated the bromide anion nucleophile in that first step of the mechanism. So imagine that bromine comes in and attacks that carbon that bears that oxygen leaving group. Okay, and this is the SN2 step. Okay, so this is how we're observing inversion of configuration. So here in SN2, the incoming bromide came in from the back face, and then we released this byproduct. Okay, and so we can replace these other 2 bromines through an analogous mechanism. We would just have another alcohol displace the bromide, have the bromide attack, and then repeat that step with the 3rd bromide. Okay, so we're really seeing SN2 as the dominant mechanism here. All right, given that, we have this good leaving group, we have a strong nucleophile and bromide. Okay, and so this reaction with PBr3 gives us an alternative to making alkyl bromides from alcohols, and specifically you would want to use them when you're converting secondary alcohols, because we can't use our previous method that we learned, which was HBr. All right, so let's just look at one example of using this reaction, and then we'll look at an analogous reaction for chlorine. So let's look at, so that's overly complicated, so let's make it that. Okay, so in this way, we can see we have a secondary alcohol. The incoming bromide would come in from the back face. So we'll see inversion of configuration. So we have that single enantiomer as our product following the SN2 mechanism. Okay, so our next reaction today that we're going to talk about is, as I mentioned, an analogous reaction, but to generate chlorides instead of bromides. So we actually use different reagents here, so we'll see that, but many of the fundamentals that we talked about for this reaction with PBr3 hold true for the next reaction, in that there's going to be an SN2 mechanism. We see inversion of configuration, only methyl primary and secondary alcohols work. Okay, so the reaction we're about to talk about is the reaction of alcohols with SOCl2, that's our chloride providing reagent, and pyridine, of which I will define here in just 1 second. Okay, so let me give you the overview of the reaction in terms of reagents and conditions. Okay, so we have our alcohol. We're going to react that with this SOCl2 and pyridine, and this is going to give us the corresponding alkyl chloride. Okay, so notice how we're doing a substitution. The chloride is taking place of the hydroxyl group. Okay, so a few things about this reaction. So only methyl primary and secondary alcohols can be used in this reaction. We observe inversion of configuration. Okay, so inversion of configuration observed. Okay, so again, this implies that we follow an SN2 mechanism. So let me define those species, SOCl2 and pyridine. And we're actually not going to talk about the mechanism, although the mechanism is in our textbook if you wanted to see, that SN2-like step. But we have some similarities in this mechanism where, we're going to convert OH into a good leaving group. Chloride's going to end up being our nucleophile, and it's going to attack from the backside. Okay, so SOCl2, what is its structure and what's its name? So this is actually a pretty common reagent, and you'll use this reagent not only to convert alcohols to alkyl chlorides, but next semester in Organic 2, you'll use this reagent to convert carboxylic acids to acid chlorides. And so this reagent you'll see again. It's called thionyl. Make sure I write that nicely, thionyl chloride. And then its structure is this. Okay, so relative to the sulfur is electrophilic in this structure. You could draw another resonance structure where you pull those electrons up on oxygen to have the oxygen anion, sulfur cation. That shows you that the sulfur is electrophilic. So if you were to look at the mechanism, you would see that the first step is for the OH to attack the sulfur of thionyl chloride. The second reagent that we are going to use here is pyridine. That acts as a base in this reaction. So it's a nitrogen containing base. It's like benzene, but one of the atoms of benzene has been replaced by a nitrogen atom. Okay, so again, in this reaction, we're not going to look specifically at the mechanism. We just need to be able to predict the product. So the things we need to keep in mind when we're predicting the products is that we can only run this reaction on methyl primary and secondary alcohols. It follows an SN2 mechanism, so the same preferences for SN2 hold true here. And so we just need to look at a couple of examples. All right, so our first example, let's look at a primary alcohol. Okay, so if you had a primary alcohol, this is a time where you could use either HCl or you could use SOCl2 and pyridine to perform the reaction. There's no stereochemistry to consider in this particular example, so we can see that we're just converting the alcohol to the corresponding alkyl chloride. And then lastly, let's do one example with stereochemistry. So let's take this example. So here's our secondary alcohol, and we're going to convert that into our secondary chloride. Okay, so notice how our leaving group alcohol is on a wedge. Our incoming nucleophile, which is chloride, is going to come in from the back side, so on a dash. And so we'd get that single enantiomer corresponding to inversion of configuration at that secondary chloride. Okay, so we can see that PBr3 and SOCl2 in terms of products are similar. They both go through SN2, they both go by inversion of configuration. They just differ in what halogen that you are making or adding. And so, you know, in terms of synthesis, like if you wanted to, for example, convert your alcohol into a chloride or bromide to then do an elimination reaction or do some other SN2 reaction like substitution, it doesn't really matter which one of these methods you were to use, okay? But the next reaction, or the next reaction we're going to learn about has a distinct stereochemical difference, although a similar purpose as the previous two reactions we've learned. Okay, so I would say in general, you know, the last two reactions we learned, converting alcohols into alkyl halides, serve the purpose in terms of synthesis of turning alcohols into better leaving groups so that you can do other substitution or elimination reactions. Okay, and you know, the two methods we've most recently learned went through an SN2 mechanism, and we observed inversion of configuration at the chiral center that bared the alcohol. Okay, so the next reaction we're going to learn is going to be an alternative way to convert alcohols into good leaving groups, but there's going to be a distinct stereochemical difference between the last two methods that we learned and the method we're about to learn. And at the end of this section, we'll go ahead and compare those methods to make sure that we can see the difference. Okay, so what we're going to talk about is, you know, really a new class of leaving groups. So at this point, you know, the leaving groups that we've seen, you know, for SN2, SN1, E1, E2 reactions have all been halogens or halides. And so there's actually other stable anions that can participate as leaving groups. And so we're going to look at those right now. Okay, so we're going to look at the formation of specifically aryl sulfonates, but other sulfonates could be used, and I'll make a note about that as well. Aryl is an abbreviation or is indicating that we have some aromatic ring, which is benzene. Okay, so first let me show you what the structure of an aryl sulfonate is. Okay, so we have some generic R group, which would be our alkyl group, and then an oxygen bound to this sulfur. And then we have some sort of group attached to the sulfur. Okay, and so this could be a wide variety of things. The specific one I'm telling you has a name. It's called tosylate, and I'll write that out in a second. But that group that I highlighted in red could be that methylbenzene. It could also be just a plain methyl group. It could just be a plain benzene. So there's different R groups that could be in place of that benzene there, and those molecules would undergo the same reactions that we're about to talk about. So this one specifically, this leaving group that we're thinking about, or this group we're thinking about, is called tosylate. Tosylate, and we abbreviate this as OTS in a molecule. Okay, so tosylate, OTS. We think about that whole thing as a good leaving group. So think about its structure as a leaving group. So it's a good leaving group. All right, so what would it look like as a leaving group? So imagine you were going to do some sort of substitution or elimination on the R group, and that whole oxygen containing species is going to leave as a leaving group. So let's look at its structure as a leaving group. Okay, so it would leave as this oxygen anion. Okay, so what is controlling the stability of that oxygen anion? Why would that be a particularly stable oxygen anion? Well, notice how there's resonance into the two other oxygen atoms, into the two sulfur oxygen double bonds. And so that's a stable anion. So it ends up being a good leaving group. Okay, so it's a stable anion, therefore it is a good leaving group. Okay, so we can use that OTS, that tosylate, which is derived by alcohols, and we'll see how in just a minute. We can use that basically as a good leaving group in all of our SN1, SN2, E1, E2 reactions we learned in chapter 9, right? And again, we could see other R groups here. So other R groups, instead of that methylbenzene, could work here. They just wouldn't be called tosylate anymore. Tosylate's the specific name for the sulfonate that I'm showing you there. Okay, so what I want to do next is think about how we're going to prepare these aryl sulfonates. We can actually make them from alcohols. And then I want to show you how you would use these versus the alkyl chlorides and bromides of the last two reactions in terms of synthesis and a synthetic strategy. Okay, so how do we make these aryl sulfonates? Okay, so preparation of aryl sulfonates. So specifically, we'll make the tosylate. Okay, so the way that we make the tosylate is going to be from the alcohol. Okay, so essentially, if we can turn, ROH into ROTS, so that alcohol into an aryl sulfonate, we have another way of converting OH into a good leaving group. So the reagents that we're going to use here is something called tosyl chloride, and I'll give you its structure here in a second. And then we need pyridine, which also acts as a base. Okay, so tosyl chloride and pyridine. And that's going to give us ROTS. So that is that whole structure we drew up above. Okay, so we have now made our tosylate. Okay, so that TSCl is called tosyl chloride. Okay, and its structure is this. Something about drawing hexanes, the rotated way is pretty difficult. Anyway, okay, so here's the structure of tosyl chloride. Okay, so tosyl chloride is used essentially to make these aryl sulfonates that we're going to use then as starting materials for our substitution and elimination reactions. Okay, so I want to just think very briefly about the mechanism. Okay, so essentially what happens in the mechanism, the mechanism is all central to this sulfur. Okay, so what happens is essentially the OH of our alcohol attacks that sulfur atom. That's kind of crazy. I'm just going to delete anyway. Okay, and so the reason why I just want to point out, and then the chlorine is going to end up leaving as a leaving group. So the reason why I'm pointing that out is just because the stereochemistry of that R group, whatever it happens to be, won't change. Okay, because all the chemistry is happening at the OH and at the sulfur. Okay, and so let's look at this in context of an actual example. Okay, and I'm not going to write the whole mechanism out. I'm not going to expect you to know it, but we need to understand the stereochemical difference. Okay, so let's look at an example that contains stereochemistry. So let's just do a pretty straightforward alcohol. Okay, so oops, I did it. So there we go. Our challenge, we have failed, or I have failed. Okay, so here we have our secondary alcohol with stereochemistry, and we're going to react that with tosyl chloride and pyridine. All right, and so since all the chemistry is happening at the OH, we're not making or breaking any bonds to that carbon. The stereochemistry of the aryl sulfonate is the same as the alcohol stereochemistry. Okay, and now we basically have this good leaving group installed at this secondary position. So let's just imagine we want to do some sort of generic SN2 reaction. So let's just say we're going to use sodium azide, NaN3. We'll throw in our favorite polar aprotic solvent to do this SN2 chemistry. Okay, so now we would observe inversion of configuration. Okay, so I just want you to think about, well, what if I wanted that azide chemistry opposite to what we're observing? Like, what if in synthesis I wanted that azide N3 to actually be on a wedge? How could I affect that in terms of synthesis? Okay, so we could start with the same alcohol. All right, but what if I use PBr3? Okay, so that would convert the alcohol into good leaving group in terms of being a halide. Okay, so now if I did the SN2 reaction, and so since this is at the step with PBr3 is SN2, I get inversion of configuration. And then if I use that to do inversion of configuration again, I'm going to do another SN2. Okay, so this double inversion then basically affects the stereochem to look like retention from this original starting material. But notice it's because I have inversion and then inversion again. Where in the first reaction, the first example, making the aryl sulfonate, I didn't touch the stereochem at the carbon that bared the OH. And so I only had a single step that was inversion. Okay, and so these two methods are similar in terms of, the overall, SN2 reaction that we're doing in the end, but they differ in terms of stereochem. Okay, so both of them, we're going to take the OH, convert it to a good leaving group, whether it's the aryl sulfonate or the bromide or the chloride, and then we'll do a subsequent SN2. The difference is in the stereochemistry. So the aryl sulfonate, when we make that, keeps the same stereochem as the alcohol, so that when I do the SN2 reaction, I get essentially inversion of configuration. In this case, the azide is on a dash. In the other method, I do inversion in the first step to convert that to a bromide, and then inversion again in the next SN2 reaction. Okay, so these two methods are similar in terms of their overall reactions, turn into a good leaving group, then do SN2, but overall they're different in terms of their stereochemistry. So that's something to keep in mind, as you're thinking about, synthesis problems and, using some of these reactions in context. Okay, so let's look at one other example of using an aryl sulfonate. So we've seen that aryl sulfonates are good leaving groups for SN2. Let's just point out that they're also good leaving groups for E2 reactions as well. Okay, and specifically I'm going to do this to do a Hofmann elimination. So let's look at this example. Okay, so let's say that we want to basically eliminate this alcohol to make this Hofmann alkene. Okay, so through some number of steps. Okay, so we can't, as we're going to learn, the dehydration of alcohols, which is our next reaction, is going to follow an E1-like mechanism and is going to follow Zaitsev's rule. And so if I want to get essentially a Hofmann dehydration product, I need to first convert that OH into a good leaving group, and then I can use my bulky base to arrive at the less substituted alkene. Okay, so what we could do here, and you could use PBr3 or SOCl2 to turn that into an alkyl halide, bromide or chloride. The stereochem actually is irrelevant here. I just wanted to point out that we can also use these aryl sulfonates to elicit E2 reactions as well. And for that matter, SN1 or E1. Okay, so here we've made our aryl sulfonate, and now I can just treat that with my bulky base, LDA or tert butoxide, to arrive at the Hofmann alkene product. Okay, so we can see that aryl sulfonates are useful for various substitution and elimination reactions, and they give us an alternative to creating the alkyl halide through PBr3 or SOCl2. All right, so we just looked at, converting alcohols to an alkene in a two-step process, basically turn it into a good leaving group and then do some sort of E2 elimination. So the next reaction of this chapter is essentially the direct dehydration of alcohols. Okay, so that's our next big reaction. Okay, so this is the dehydration. So dehydration means we're removing water. Okay, so dehydration. So think about removal of water from the system. Okay, and so this actually ends up being the reverse reaction of alkene hydration. Okay, so dehydration and hydration are opposite reactions. One's adding water, one's removing water. Okay, and so in terms of mechanism, we're going to observe something interesting about this dehydration mechanism and then acid catalyzed hydration of alkene mechanisms that we already learned. Okay, so let me just talk a little bit about the reagents and conditions for this reaction. Okay, and I'm not going to give any specific molecules at this point. Let's just look at the overview of the reaction. Okay, so we're going to have an alkene or an alcohol, and at the beta position, we're going to have a hydrogen, and that is where how we're going to remove water. So we are going to treat with H2SO4, and we need to heat this. And you will oftentimes see the notation minus H2O, and I'll talk about that relevance here in just a second. And the product of this reaction is the alkene, and we have eliminated water from our alcohol to create the alkene. So we removed an H and an OH and formed a pi bond between those two carbons. So that's called a dehydration. Okay, so this reaction, okay, so let me just draw these two molecules again. And I want to talk about the equilibrium that is established between the alcohol and the alkene. Okay, so we have the forward reaction we're talking about is dehydration, and then we have the reverse reaction, which is basically alkene hydration. So in the forward direction, okay, so from the alcohol to the alkene, our reagents were, so I'll put this on top, I guess. So in going in the forward direction, we needed H2SO4 and heat, and we removed water. Okay, if we wanted to go the other direction from the alkene to the alcohol, we used H2O, we added H2O, and basically some sort of acid catalyst. So we could use H2SO4, that's fine. Okay, so basically this is directly related to a principle, Le Chatelier's principle, that you learned back in general chemistry. So these reactions are in equilibrium with one another, the forward and the reverse reaction. And so how we can control the concentration of our products or the position of the equilibrium, in this case, we're going to do that by either adding or removing water from the system. Okay, so in the, the direction that's going from alkene to alcohol, we know we can just add water as a reagent. Okay, but what about going from the alcohol to the alkene? How do I, quote unquote, minus H2O? Okay, well, it turns out that there's actual laboratory glassware that we can run these reactions in that allow us to take advantage of the boiling point difference between water and organic solvents, and they allow us to basically selectively remove water from our reaction mixture. So we literally can minus H2O. We can remove water from the system. And as we remove water from the system, that pushes the equilibrium of this process to the alkene. We prevent the back reaction to the alcohol starting material. So when we look at the mechanism, we'll talk about, well, if we remove water from the system, we're no longer able to do the back reaction to the, starting material that we started with. Okay, so let's go ahead and look at an example of this and talk about the mechanism, and then we'll talk about some issues related to the regiochemistry. Okay, so the example that we're going to use is this tertiary alcohol. And we're going to treat this with H2SO4, and other strong acids work here. I think our book likes H3PO4. And then I will often write this minus H2O to remind you that we're doing a dehydration reaction here. Okay, so we're going to form our alkene. In this case, these 3 carbons were all the same, so I only had one potential product in terms of constitutional isomerism or regioisomers, and didn't matter which direction you dehydrated towards. All right, so let's just assume that this is going to go by either an E1 or an E2 mechanism. Just looking at the reagents, what do you think? What does an E2 reaction require? So an E2 reaction requires a strong base and a good leaving group. We don't have either of those things. An E1 reaction, requires, I guess essentially a weak base, and it does require a good leaving group, but notice how we're under acidic conditions, and we learned that we can convert OHs into good leaving groups under acidic conditions. So I think E1, just using what we've already learned would be the best candidate reaction to undergo, and that's what we're gonna see here. Okay, so our first step of the mechanism is gonna be to protonate. So our acid is H2SO4, here's that structure of sulfuric acid. And it's going to go ahead and do our acid base step. And this serves the role in terms of elimination of converting OH into a good leaving group. And I'm going to show all of these steps as equilibrium. Usually I avoid, I don't necessarily ever talk about what type of arrows, equilibrium, or, forward direction arrows that we're using, but I want to talk about the equilibrium related to Le Chatelier's principle as we go through this. Okay, so I generated that protonated alcohol and then the HSO4 minus anion as the conjugate base of sulfuric acid. So now I've converted that water and that OH into a good leaving group, which is water, and now I can follow my elimination mechanism. Okay, well I don't have a strong base around, so I'm not going to do E2 elimination. So from here we're going to follow the E1 mechanism. So what happens next in the E1 mechanism? What intermediate do I go through? We go through a carbocation, right? Okay, so we're going to form the carbocation. So I'll put that down here. Okay, so here, as we're going through a carbocation, and this is an E1 mechanism, check for rearrangements before you proceed in the mechanism. And then from there, what we're going to do, we also generated this water, okay, and we are going to remove this beta hydrogen. Okay, so we could use either HSO4 minus sulfate anion, or we could use water as the base here. Our book uses water, so that's what I'm going to use. Okay, and so water really had 2 fates, right? Water could have removed that proton, or water could have attacked the carbocation. And if water attacked the carbocation, we're just going back, in this reverse direction in that way. Okay, so water is going to remove that proton, and that actually gets us directly to our alkene product. Okay, so as we proceed in the reaction though, we're going to end up removing water. So once we've generated this protonated water, it can then be used as the source of acid, in this step up here, and then we'll, eventually regenerate H2O. And so, as we start to slowly remove water from the system, we eliminate the chances of water acting as a nucleophile, and adding into the carbocation at that step. So as we remove water, we prevent each of those back reactions and we push the equilibrium of this entire process to the alkene. Okay, so that's one thing I wanted to talk about is like, why are we functionally removing water and how do we do that? The other thing is, let's look at this mechanism a little bit more closely. Specifically, if you were to take this alkene and react it with H2O and HCl, and you were going to do the alkene hydration, I want you to think about what intermediates would form. Okay, so if I did an alkene hydration, what is the first intermediate I form? So the rate determining step was formation of the carbocation. And then what happened? Well, then water attacked the carbocation and I got to this structure here. And then what happened? I deprotonated that protonated alcohol to get to my final product. So notice how these, forward and reverse reactions, okay, so this forward and reverse reaction between the alcohol and the alkene, they have the same mechanistic intermediates. They're just occurring in the reverse order. So that has a name, and you'll talk about this a lot more in organic chemistry too. It's called microscopic reversibility. And it basically says these two reactions that are, at equilibrium, the forward and the reverse reactions, their mechanisms go by the same intermediates, but occur in the opposite order. So you'll see other examples of that next semester when you think about, I think specifically you'll see that in the carboxylic acid chapter. Okay, so now we've looked at the mechanism and we talked about how, this is essentially, I didn't write this, so let's do that here, but basically we're looking at an E1 mechanism at this point. And this is one time where we don't have the problem of SN1 as a competition, because as we eliminate water from the system, we don't have that water to act as a nucleophile to give us the SN1 mechanism. So this is a time, one of the only times where we will exclusively draw an E1 product without being hindered by the corresponding SN1 product. Okay, so then thinking about E1, we know it goes through a carbocation. Okay, and we could check for carbocation rearrangements. The other thing I want to think about is the regioselectivity. Okay, so what is the regioselectivity of an E1 reaction? Okay, so is it a Zaitsev or a Hofmann process? Okay, so hopefully you said Zaitsev. So what does that mean? Does it go through the more or the less substituted alkene? So it goes through the more substituted alkene. So let's look at an example or two of that. Okay, so here's our first example. So we're going to take this alcohol and we're going to treat it with H2SO4 and heat. We'll remove water from the system to push the equilibrium towards the alkene. Okay, and so let me just count the carbons here so that we can talk about them and think about which direction we formed the alkene. Okay, so if I'm going to eliminate, I can eliminate towards carbon 1 or towards carbon 3. So which one of those would be the preferred alkene? Okay, so the preferred alkene in this case would be that di-substituted alkene. Okay, so we're following Zaitsev's rule. Okay, so let's just make a note that it's regioselective and it follows Zaitsev's rule. Okay, so let's look at one last example of this reaction. Okay, specifically, let's look at something with a carbocation rearrangement, since we haven't seen that in a while, just to make sure that we can still predict the products there. Okay, so let's look at this reaction, and we're gonna do our dehydration with our strong acid, heat, remove water. Okay, so what I would probably do just to make sure that you are, checking for your rearrangements is, let's go ahead and draw the carbocation that would form. So let's just imagine we protonated our OH and we turned it into a good leaving group, and then we would generate that secondary carbocation. Okay, but we're a secondary carbocation directly outside of our strained 5-membered ring, so we can do a ring expansion rearrangement to get us to the corresponding 6-membered ring. Okay, so now we've generated that tertiary carbocation, and now we can think about what the most substituted alkene could form is. So we could either form, there's several different products we could form. So the minor products we could eliminate to this side or this side. That would give us the di and tri-substituted alkenes respectively. But what we're gonna observe is elimination towards the tetrasubstituted or to this tetrasubstituted alkene. So the major product of this reaction would be that. Okay, so if you're going to predict the minor products from these reactions, you would consider the carbocation that's formed and think about the different eliminations you could perform from, either the original carbocation or the rearranged carbocation, right? Okay, so this highlights a ring expansion rearrangement in the context of dehydration. Okay, so one last thing about dehydration. So, if you're thinking about it as an E1 mechanism, remember what the preference for E1 is. The more stable the carbocation, the faster that reaction would be. So if you had to rank alcohols and their ability to undergo a dehydration in terms of rate, the more stable the carbocation, that faster the dehydration reaction would be. Okay, so in the last 10 minutes or so here, I just want to introduce the next series of reactions. So all we have to cover really before our exam is the oxidation reactions of alcohols. So I want to introduce that topic, oxidation of alcohols, today, and then we'll look at the specific reagents on Monday, and we'll definitely be able to finish up exam material on Monday. And then my plan for the rest of Monday, if we have extra time and potentially even on Wednesday, is I will maybe work through some synthesis problems instead of a lecture where I'm telling you about new information. All right, so let's go ahead and introduce this last topic of this chapter, which is the oxidation of alcohols. All right, so we've seen oxidation and reduction reactions before. We saw oxidation of alkenes with ozonolysis and the reaction with OSO4. We've seen the reduction of alkenes to alkanes and the reduction of alkynes to either alkenes or alkanes. And so what we need to first think about is, the oxidation of alcohols. What are the potential products, oxidation products of alcohols? Okay, so I want to break this up into the various alcohols that we could perform an oxidation on. So first I want to look at a primary alcohol. Okay, and I want to do the oxidation. Okay, so in oxidations, I basically am going to remove hydrogen or add oxygen. So thinking about the structure of our primary alcohol, we have these two hydrogens that could be removed as we go through oxidation. Okay, so one potential functional group that I could arrive at for the oxidation of alcohols would be this, where I've basically converted this to a carbonyl, and I've removed basically one of the hydrogens and I've gained one bond to oxygen. So what is this functional group? It's an aldehyde, right? But I still have this one hydrogen that I could continue the oxidation with. All right, and so if I used different oxidation conditions, I could continue my oxidation to the corresponding carboxylic acid. Carboxylic acid. Okay, so whether I convert my primary alcohol to aldehydes or carboxylic acids, this will depend on the reagent. So it depends on oxidation conditions or reagents. Okay, so we'll learn a few different oxidations. Some of them will oxidize primary alcohols to aldehydes. Some of them will oxidize primary alcohols to carboxylic acids. Okay, so that was primary alcohols. So let's look at secondary alcohols next. Okay, so for secondary alcohols, we would have something like this. Okay, so our secondary alcohol. So the first thing I want to look at is, well, how many hydrogens are at the carbon that bear the OH? Just one, right? So there's only one candidate hydrogen I could remove here in the oxidation. I'm not going to break a carbon-carbon bond between the carbon and the R group, whatever it happens to be. Okay, so there's only one oxidation product possible for secondary alcohols, and that's going to be a ketone. That wasn't even selected, so I don't know why it erased it. We'll see if it erases again. Okay, so there's only one possible product for oxidation of secondary alcohols, and that is a ketone. Okay, so regardless of oxidation conditions for a secondary alcohol, we will arrive at a ketone. Okay, so this would be, all the oxidation conditions that we're going to learn for secondary alcohols will give us a ketone. Okay, and then lastly, let's look at a tertiary alcohol, where we have these three R groups that are bound to the carbon that bears the OH. So here we can do oxidation. Okay, Well, are there any hydrogens at that carbon that bears the OH that we can remove in oxidation? There's not, right? So I can't increase the number of bonds to the oxygen that's there because I'm not going to break a carbon-carbon bond. So there actually are no oxidations of tertiary alcohols that we have to worry about. All right, so tertiary alcohols do not undergo oxidation. Okay, so really, what our goal for Monday is going to be is to figure out what reagents and conditions oxidize primary alcohols to either aldehydes or carboxylic acids, and then think about how that operates on secondary alcohols to give ketones. Okay, so I think we have 3 or 4 oxidizing conditions that we will have to talk about. And then as I mentioned, any extra time we have on Monday, I will go ahead and work through some alcohol-related synthesis problems. So if you wanted to just get a jump start over the weekend, for finishing up this chapter, you'll just want to look at those oxidizing conditions that we'll go ahead and talk about on Monday. All right, I hope you guys all have a good weekend, and I will see you guys all or talk to you guys all on Monday.